Good morning, everyone. So, as you know, that in the last class we have seen about the equations, and we have discussed some of the idea about how you are going to acquire the data and how you are going to predict or how you are going to forecast your production based on the data you are having. So we'll continue to a little further. Yesterday we have seen the application of the volumetric calculation and some of the parameters based on the design, based on the well spacing. Okay, and we have also seen that how the internal properties, reservoir properties, can affect the production based on the volumetric calculations. Okay, so today we'll start with a little bit about the material balance equations. Yesterday we have seen about the volumetric calculations and their assumptions, various assumptions, and some of the results. Okay, so in continuation to that, so the third part is the simulation. So simulation is a total process which will be continued for any time of the total duration of the production life or the reservoir life. But for material balance equation, it is very rigorous process. It is going to give you very accurate results. Okay. The difference between the volumetric and the material balance equation is that volumetric is going to take about the volume of the gases adsorbed. That means it's based on the whatever the volume of the gases that are already in place, and based on the recovery factor, how much of that you are going to collect, your production will be dependent. Okay, and the material balance equation, as I mentioned yesterday also, that whenever you are going to produce the gas, it is not only the pressure is only reducing. Depending on the pressure, the pore volume, the compressivity, the soiling effect or the shrinkage effect, the aperture dimension changes, the permeability changes. Okay, and the gas saturation, water saturation, the permeability, the relative permeability of the gas and water, these are also changing. So there are many more parameters which are not constant, which are also changing with production because the pressure is changing. Okay, so material balance equation is going to take care of all those changes. Okay, material balance equation, if you follow the rigorous process, it can simultaneously solve the different parameters. It is first introduced by scientist King, as you can see from some of his work, that it is going to comprise of some different parameter, and there are obviously having some assumptions for this, and based on this you can easily accurately calculate about the volume of the gases and the volume of the gas in place and the volume of the gases are produced. Okay, because this material balance equation is going to consider about the volumetric changes, about the pressure changes, permeability effect, and the pore volume capacity changes. Okay, so we'll be learning shortly about this because there are so many equations. As you can see, there are equations, there are different parameters, but all those things details we'll be learning in the later part when we'll be going to discuss about the experimental part and the simulation part in a detailed way. Okay, but for now, just some idea for you, and then you'll be able to understand after the end of the fourth chapter. Okay, so let us see first what are the different assumptions which is going to be important for material balance equation. Now first is that you have to assume that the equilibrium between the free gas and the adsorbed gas in the reservoir and the saturation conditions with respect to the isotherm. Now, as I mentioned earlier, that depending on the gas saturation, whether the gas is partially saturated, very less saturated, 10%, 20%, or 50%, or 80%, or totally saturated, it's 100%. Based on that, the properties of the gases will vary, properties of the coal and the gas in place capacity is also varying. Okay, and obviously, if you see the other isotherm in the earlier cases, whatever I have shown to you, you will see that If only the gas is totally, the coal bed methane is totally saturated with the gas or the methane, then only the initial gas content, which is shown here, it will lie actually on the isotherm graph for that particular reservoir at that particular temperature pressure condition. Okay. If not, that means the reservoir is undersaturated with the gas, because it is going to give you lesser gas, and if it is undersaturated, so obviously withdrawing the pressure or withdrawing the water and reducing the pressure will not directly give rise to the water or gas. First you have to reach that much of pressure, you have to go down from this pressure zone to this pressure zone, so that you are going to reach the critical gas dissolution pressure of particular gas of the particular reservoir. And then with the critical dissolution pressure attaining, when you are further going to reduce the pressure of the reservoir below this critical dissolution pressure, then only the gas production will start. Okay. And again, the gas production will be possible only up to the point of abandonment pressure. Once the gas pressure, the reservoir pressure has reached the abandonment gas pressure of the reservoir, then the further reducing of the pressure by taking out the water or by pumping out the gases, it will not give any gas production. Okay, and that much gas, as you can see here, approximately 100 SCF per ton, this amount of the gas is retained within the reservoir. You cannot take out. Okay, it only be available if you are going to collect the cold sample from the reservoir, and you are going to fracture it, you are going to take it by the desorption canister testing, and then you are going to take the gases. You can store the gases. Otherwise, total recovery is not possible. Okay. Most of the cases it is observed that 75% of the recovery, or sometimes 70% of the recovery, is more or less achievable. Okay, in the conventional reservoir. Now, to continue this, there are so in this case of the gas production, you have to know about the free gas fraction and the adsorbed gas fraction. Why these two different fraction has to be known? Because you know that the coal bed methane reservoir is a dual porosity model. Okay, so the primary porosity is comprising with the micropores, mesopores, and the macropores, and where the gases are stored in an adsorbed state, and maximum amount of the gas, mainly 90%, mainly methane, approximately 90% or 95% or sometimes more than that, are stored in the solid coal matrix. Okay, whereas the other 5%, or less than 5%, are stored in a free state in the natural fractures, which are the secondary porosity, which is comprising of the face clits, butt clits, and the other tertiary clits and the natural fracture system. So that's why the coal is called the dual porosity system. And so the fraction of these two, what amount is fixed with the adsorbed state, what amount is stored in the free state, you have to know very carefully. And this material balance equation is giving you the idea about how to calculate this. Okay. So obviously, if you know what amount of the gases are adsorbed, what amount of the gases are in a free state, so obviously you will be able to know about the gas saturation of the particular reservoir at a particular temperature pressure condition. Okay. The next point is, it requires accurate estimate of key reservoir data such as pressure, desorption isotherm, permeability characteristic, etc. So accurate measurement is required, such as pressure. So because the pressure is the main criteria based on which the gases will be adsorbed or desorbed, or gases will be transported, because permeability and the adsorption, both of them are the pressure dependent process. Desorption isotherm has to be accurately known. Why? Because if you have also seen that if there is changes of the desorption isotherm graph shape, then obviously your production value, whatever you are getting, there may be chances of the error. Okay, so for that thing, what you need to do, you have to accurately measure this. How we are going to measure? whatever the desorption isotherm you are going to prepare, that has to be collected either by the desorption canister testing, okay, or by the field data. When in the field data, when you are going to dewater the borehole, so from there also you can collect the total desorption isotherm for that reservoir particularly, or suppose for some coal sample, if you are going to test in the laboratory, you are going to inject, or suppose you are taking out some coal sample from the core barrel and you are putting in a desorption canister, from the testing you will be able to know about the desorption isotherm. Why it is important to know the desorption isotherm? Because until unless you are having the desorption isotherm, you will not be able to know about the saturation or the undersaturation or the total saturation of the reservoir with the gas. Because it is only when you will see that your established desorption isotherm lying above of the initial gas content or initial gas in place, then only you will be able to know that okay, reservoir is undersaturated. If your desorption isotherm graphs lying exactly on the initial gas content point, then you know that okay, it is totally saturated because it is lying on that graph. So at that particular pressure, whatever isotherm graph is forecasting to have that much amount of the gas, your initial gas content is exactly showing that amount of the gas. So that is totally saturated with the gas at that. Okay. So this is important, and then is the permeability characteristics. Permeability characteristics means the absolute permeability and the relative permeability characteristics. How with the saturation with the individual water and the gas permeability will behave. And again, whenever there is a gas production, the different fraction of the water and the gas is going to be produced. So how they are going to be in these two different phases, how their internal interaction of the gas and the water is going to take place, and how it is going to affect the permeability, because with that permeability the production will be considered. Next, third point is the assumes pseudo steady state desorption characteristics. Now, desorption characteristics means you are decreasing the pressure, your gases are coming out, and so with the volume of the gases are coming out, it is going to after then the diffusion will happen, and then there will be Darcy flow so that you can collect the water. Okay, so it is desorption isotherm characteristics. Okay, desorption characteristics. Steady state means fixed with time, constantly at a constant rate. Steady state, whereas dynamic state means it is changing with time. Okay. Now it is mentioned as the pseudo steady state. Okay. Now why these assumptions of the pseudo steady state is important? If you are going to consider initially, you have to consider that whatever your reservoir properties are there, they are not changing with the time. But actually it is not a steady state. That's why it is called a pseudo steady state. It is very variable, but for your initial consideration, you have to consider the simplest algorithm, simplest condition, that all of the things, all of the properties are not changing with the time. But then you are totally having the isotherm graph. Then you will increase the parameter with time, and then you will see the behavior that if the dynamic state is available, how this gas production will change and how it will behave. Okay, just like in the rock mechanics, you must have heard about the Kyle and Dan sample. All of you know about the Kyle and Dan concept for rock mass and then intact rock. You have
Yes,
studied.
sir.
Okay, so Kyle and Dan are the two simple acronyms which are going to give idea about the what are the simplest condition, what are the laboratory condition, and what is the most field condition you need to consider before you are going to design for any structure. So like that way, you have to consider that it is steady state, whether you would all know that it will be not a steady state. So assume that pseudo steady state desorption characteristic. So you have to assume that initially the steady state, just like in the phase 1, we are going to consider that the water production is going to be constant. It is not possible that the water production rate is going to be constant, because if you are going to take out the water, the pore water pressure is going to reduce. So obviously there has to be some changes in the permeability. Okay, so whenever you are going to see this type of concept, you have to be very clear about the different assumptions. Okay, the fourth point is that requires accurate estimates of water encroachment. Water encroachment means about what is, you know, about your total reserve CBM reservoir area, and then depending on the water saturation, depending on the network of the fractures, you have to have the idea that whether all area is totally filled with the water or not, whether there is any type of seepage, whether there is any type of water reservoir available in the nearby area. Because whenever it is available, you have to you have to pump out more water to get the gas production. Or maybe that water with very high head, very high pore pressure, it can create the fractures into the rock. Okay, so you have also studied the soil mechanics, some part of the soil mechanics. So you must have understood the two different important terms, which is called the drained shear strength and the undrained shear strength. You know about this drained shear strength and the undrained shear strength?
Yes, sir.
Okay. So if this is the case for the soil, where one type of water can migrate and another type of water cannot migrate, so they are going to give the extra pressure. For rock also, if there is a natural fracture system, so what intercepting fracture systems, so water may percolate from one area to the another area. But if it is not possible, the fractures are not interconnected, or there is a other type of filling material inside the aperture, discontinuity aperture, so that there is a no place for open channel. So then what will happen? The water will not be able to move and it will give the pressure. So obviously the pore pressure is going to change, and this amount of the pore pressure is going to again significantly changing the effective stress consideration, which will again going to destabilize your reservoir characteristics from the mechanical point of view. Okay, so this type of things you need to consider for the water area. So what is the water channels, or what are the total water encroachment area, if there is any high flood level or aquifer available, so those type of things. And then models the wellbore damage or stimulation using the skin factors, okay, which may not be applicable for the hydraulic fractured wells. Now skin factor I have discussed you in the earlier. The skin factor is a very typical phenomena which is observed in the production well or when you are going to do the drill well. Okay, so suppose that you are going to drill a borehole. So if you consider the periphery of the borehole, okay, so there is a rock. So obviously, whenever the diamond drilling or the borehole is drilled, okay, it is not always the case that you are going to get a smooth periphery of the boundary. In that case, whatever fractures are going to intercept into the excavation, that means in this case into the borehole. So you will find that if there is any other rock strata which is very much strong, then the water, the inside water cannot be coming out into the borehole. But if it is a very much connected, like a coal bed methane reservoir, like a coal mine situation, you know that for coal mine it is very much prone to the fractures. Okay, so water connectivity will be there, and the more you are going to drill, all the water will be coming into the borehole and it will be accommodated into that borehole. So you have to take out the water before you are going to do any further drilling. So why this is important? Because if you can see the boundary, you have to imagine the boundary of the borehole you have taken out, you have drilled, and if the boundary of the borehole is not actually proper, that means proper means it is totally like a cemented surface, so that if you are pouring a water, the water will be staying in the borehole, it will not be percolated or permeated into the surrounding strata. If that is the case, that it is totally impervious, okay, so that means when you are going to collect the water from the CBM reservoir, water will not go into the side direction, water will be directly collected to the surface. But if there is a cracks, or there is a fracture, there are drilling induced fracture, there is a typical shear fracture for the drilling. Okay, if those fractures are present, and obviously those fractures are open to the excavation. So if you take a borehole camera, if you see the surface of the borehole and you are plotting in an area over a map, you will be seeing that there are numerous fractures available. So depending on the orientation, depending on the dimension of that fractures, properties of the fractures or the discontinuities, okay, what will happen? When you are going to take out the water has a tendency to go into the different direction also, because water is under pressure. Okay, so in the surrounding direction, okay, if it is going to find any open channel, so water will be going to transfer into the cross direction. Okay, you know about the cross flow and the normal flow, so it is going to give rise the cross flow. What will happen then? If there is a cross flow, so some amount of the water is again going to return to the reservoir, some amount of the water is again going to flow into the other areas. Okay, and suppose this is the case of the gas, so gas are not coming directly to the surface, it is somewhat going to enter into the side direction, and obviously as some component are going to be withdrawn, so it is actually total pressure is going to reduce. This damages, these fractures, the created fractures, depending on the actual cemented surface in the actual case, and the real case which is created. This is called the skin factor. This is called the skin factor. The more damages or the more incremental skin fracture is obviously we don't want, because in that case our gases will be escaped into the side directions. Okay, so these skin fractures should be minimized, and you have to see the simulation, because at what pressure, as you are going to take out the sample, as you are going to take out the gases from the very depth, suppose 2 kilometer, you know that when you are going to the surface, the pressure is going to reduce. If you are going to under the surface at 1 kilometer, 2 kilometer depth, the pressure is going to increase, because there is a hydrostatic gradient. Okay, there is a hydrostatic gradient, there is a geothermal gradient. Geothermal gradient means if you are going to the underground, your temperature, gas temperature will rise. So that is called the geothermal core gradient. So depending on the variation of the depth, the stresses will change, the pore pressure will change, and then if there is a numerous fractures which is interconnected into a borehole, so this, when the water or the gas pressure will go into the side direction, it will be again going to reduce the pressure and the production. So you have to have the idea about the skin factor, and as it is not actually perfect unless you are doing the reinforced concrete or the concrete structure, okay, in the periphery, just like a shaft sinking process, it will not give you the actual recovery. So that's why skin factor has to be maintained or has to be known. So that's why these important things you need to understand for the material balance equation. Otherwise, your calculation will be wrong. In the next segment, predicting the deliverability of a dewater coal bed wells. This chapter, this discussion, I am going to skip now, because you have some idea about the data acquiring and the forecasting and the different methods. Okay, some idea you have got. But this prediction at this point I am going to skip, because I'll be coming back into this when I'll be discussing with you about some part of the simulation. Okay, so for this time being, this predicting deliverability of a dewater coal bed reservoir wells. Okay, I'm just going to skip it. Okay, and but at the same time, you please see the table 310. Okay, in this table 310 and figure 322. Okay, this is for your understanding. Obviously, you will, if you see these graphs or if you see this table, they have shown you some data. Okay, they have shown you some data and some graph how to do the prediction. Okay, so please look at the table 3.10. You will see that if you are going to collect about any reservoir data or about any oilboard data, what are the different data that are available? Okay, and please, you are engineer, so obviously you don't forget about the units. Okay, so the area, the net pay is the net pay thickness. The thickness of the coal seam is the original thickness. The net pay thickness is among the in the total thickness, how much is actually going to give rise about the production, whether you are totally extracting or that some part of you are extracting. So that net pay thickness is required. Okay. Then the fracture porosity, gas permeability, initial water saturation, and the Langmuir volume, Langmuir pressure, and the Langmuir pressure constant. Okay, the Langmuir volume is defined as the as I mentioned, it is given by the VL, capital V, and suffix capital L. Langmuir pressure is capital P, and then capital L in the suffix. Whereas Langmuir pressure constant, which is the reciprocal of the Langmuir pressure. So Langmuir pressure constant is given as B, expressed in small b, which is equal to 1 by capital PL. Okay, Langmuir pressure constant is reciprocal of the Langmuir pressure. Okay, then you have to assume some coal density, initial reservoir pressure, skin factor. See, skin factor is always dimensionless because it is going to give you the ratio giving you the idea about how much it is having the damage. Okay, how much it is having the damage from the ideal condition. Okay, non-Darcy flow coefficient, it is for the permeability. Flowing bottom hole pressure. Bottom hole pressure means at that point of the reservoir, at the end of the borehole, what is the total pressure available, and at the surface, what is the total pressure available. There are two different pressure of a borehole: surface borehole pressure, surface pressure, and the bottom hole pressure at the total depth. Okay, then the reservoir temperature, wellbore radius, the boundary radius. Okay, wellbore radius is the borehole radius, whereas the boundary radius is the total reservoir radius. Okay, if you imagine a zone of influence of a borehole. Okay, and then the water rate and the water influx. Okay, how much rate or the how much water you are going to send. With this data, if you see the following graph, figure 322, you will be able to see that they have given some idea about the forecasting. They are in the right side of axis, it is totally for the cumulative gas production with billion standard cubic feet per day. Okay, it is BSCF. Okay, whereas the two left side graph is going to give you the 1000 standard cubic feet per day and reservoir pressure. Okay, so they are going to consider the reservoir pressure and the gas rate production pressure. As you can see here, there is no water condition they have shown. Okay, they have just shown you the gas. Now you can see readily that as the reservoir pressure, as the average reservoir pressure is going to reduce, you will see that the gas production rate is going to decrease. Okay, you can see that the empty square holes. Let me just increase the graph resolution. Yes, this square holes are the gas rate per stage. Gas rate per stage, whereas the right side graph is showing you the cumulative gas production. Okay, and again the black icons are for the black markers are for the average reservoir pressure. So as you can see that the reservoir pressure decrease rate and the gas production decrease rate, how much it is going to vary. Okay, you may have some confusion that I have always told that the gas production is somewhat increasing after when you are going to reduce the initial gas pressure or the water pressure, reservoir pressure. So here also you can see that the gas production, cumulative gas production is going to increase. Whereas if imagine the situation then when your water is going to be stopped, water is saturation is very low and the gas production is coming. So obviously there will be a situation that when at the end of the second phase, the peak gas production stage has already reached, and then your gas production rate is going to reduce. So this is the case Okay, this is the case you are getting. And cumulative gas production means with time, starting from the zero, with years, what is the total gas production? Okay, whereas this gas rate is going to give you the idea about per day production for every stage. Every stage means suppose when you are going to get 1000 kilopascal, what is the pressure? When you are going to get 950 kilopascal, what is the pressure gas rate? When you are going to get 900 kilopascal, what is the gas rate? And then for each pressure stage, they are going to plot with time starting from some zero. So this is the gas rate production. And then if you are going to sum all of this, so from the starting, what is the total gas production? Then you are going to get the cumulative gas production. Okay. So this is to give you some idea about how the data is going to collected, and with the data, how much you are going to infer the production. Okay. So with this discussion, this is the summarizing of this chapter. With this discussion, your third chapter is done. Okay. And today we'll start the most important chapter, which is the fourth chapter. It is a little bit bigger chapter. Okay. And I'll be going very slow, and you all need to be very careful and very attentive for this chapter, because this is exactly the total detailed analysis of the reservoir from storage point of view and the transport point of view. But before I am going to start this, let me ask you if one of you are having any question. Please ask if you are having any question at this point of time. I can see some of the students are putting a hold on the class. I don't know whether they are sitting on the in front of the computer or not. They have just put the switch on and they have just left. Okay. So let me tell you that when I am going to take the attendance, obviously I'll be not just taking all the time, and I'll be not taking always the attendance after end of the class. So in that case, if I find that somebody has joined and after 10 minutes he has left, so I'll erase his attendance. Okay. So keep that in your mind. It is not the case that you will be taking only 10 minutes class and you will be leaving for 20 minutes, and then at the end you will be joining again for 10 minutes, and or maybe during the class you will be putting a hold and then you will be doing your work. It is not allowed. Okay. So let us join with the fourth chapter. Let us start the fourth chapter. So this chapter is going to give you the idea about the coal bed methane reservoir properties. Okay, the detailed analysis. Now, from the initial few chapters, we have seen that the coal is having with the coal matrix and some natural fracture systems. Okay, so it is always a source reservoir. We have also seen that the coal is a source reservoir and a reserve storage also. Okay, why source? Because it is going to generate the gas. Okay, and it is also a reservoir because it is also going to store the gas. So it is also a storage. And depending on the structure, we have seen that the matrix is comprising of the pores, okay, where the maximum amount of the gases are stored in the adsorption state, and the fracture systems are comprising of the natural fractures, the face clits, the birth clits, the bedding planes, and the tertiary clits, and obviously which is naturally formed. And here the gases are stored very less than 5% or so in a free state. And it is called a single permeability model because there is no flow, no fluid flow is allowed within the pores. It is a single permeability model generally assumed. So no flow or no fluid flow is allowed within the pores. Fluid flow is only allowed through the secondary porosity, which is the natural fracture systems. Okay, and obviously governed by the Darcy flow after the scientist Darcy. Okay, that's why the permeability is also having the unit of a Darcy. Whereas in between this, there lies the diffusion. So we have also seen that the coal bed methane is a process Okay, reservoir production of the gas is a process of desorption, diffusion, and the Darcy flow. So you can see that it is a 3D process. Desorption, so when you are going to take the pressure out, at first the gases will be dissolved following the desorption isotope or the sorption-Langmuir isotope. Okay, so the first it will be dissolved, then second, with this desorption, the gases are now changed from the adsorbed state to the free state, but they are inside the pore. Now they are going to move to the pore wall boundary and they are going to transfer themselves, diffusing from the pore wall boundary to the open boundary of the natural fracture system. And there lies the concept of the gas diffusion. Okay, and then when the diffusion, which is governed by the concentration gradient, when the diffusion process is done, the gases are coming into the natural fracture system at a free state condition. And then again the Darcy flow is being governed by the pressure gradient, okay, with the length, how much pressure is available. So again the permeability come into the place, and then with this permeability gases are going to flow into the surface. So if you are going to see if you are going to read about the text, or if you have correctly understood about the concept, there are two main concepts which we need to be very careful. First is about the storage, and the second is about the gas flow. Okay, that means first is the storage and second is the gas production, how much of it will come. Both of them are going to give you the good recovery. Earlier you have seen that estimation of the gas in place is also very much important, because the recovery factor will be depending on your initial gas in place calculation. And then about how much initial gas in place you are going to produce, that will give you rise about the gas production. So the gas production, for the gas production you have to have the transport system, you have to have the transport properties, you have to have a permeability, good permeability, usable properties. So that's why the permeability or the transport properties is also you need to analyze. So as you can see here, that the gas production from the coal bed methane reservoir must first move through the coal matrix to a nearby natural fracture systems, and then through the reservoir natural fracture system to the well. Okay, so if I summarize, to determine the volume of the gas in place, we need to know this gas in place and the potential gas recovery. As a function of the pressure, the coal matrix properties have to be evaluated. Why? Because it is in the coal matrix the gases are stored. Okay, so what are the different properties of the coal matrix you need to know? They have given two tables. Table 4.1 is the properties of the coal matrix, where you will see that you have to know the soft gas storage capacity, what is the initial gas concentration, soft gas composition. Composition means the gas saturation, whether it is only the methane, whether it is methane and carbon dioxide, whether it is methane, nitrogen, carbon dioxide, or there are other gases. What is the concentration? What is the ratio? Okay, then the soft gas volume. Soft gas volume is the total volume of the gas that is being in the soft phase. Okay, the gross thickness, because depending on the thickness only the gases will be stored. Actual reservoir coal seam thickness you have to take care. And the diffusivity. Why diffusivity? Because with this diffusivity of this pore wall, the diffusion will occur based on the concentration gradient, and this diffusivity or the diffusion coefficient will dictate that with time how much mass transfer, which is called the concentration of the gases, are going to transfer from the pore wall to the natural fracture system. Okay, so these are all the related property of the coal matrix. We'll see one by one. In the second case, to determine the gas and water production rate from the coal bed methane wells, the properties of the coal natural fracture system must be evaluated. So again, like the storage, which was very much related to the coal matrix, for the flow, as there is no flow into the pore system, so flow conditions are totally governed by the natural fracture systems. So you need to know the natural fracture systems in a more detailed way. So again, the table 4.2 will give you some of the properties. What are the properties? The sources in both the tables are going to give you the idea from where you can collect the data. You can see that some of the data has to be collected from the laboratory experiments and obviously from the field studies. Otherwise you will not be able to get the initial data. And simulation is only fruitful when you have some initial data. If you are not having an initial data, you cannot go for the simulation. It will be erroneous. In the table 4.2, you can see the natural fracture system properties. What are the properties are coming? First is the pressure, obviously, because it is pressure dependent process flow. Okay. Then the absolute permeability, because it is the important parameter through which the gas production will dictate. And then C, the relative permeability. Relative permeability is coming when there are two different phases or more phases. If there is only a single phase of water or the gas, the relative permeability will not come. Okay. The fourth is the effective thickness. Effective thickness or the net pay thickness, you will see that it is not always the case that we are going to do the consider the production from total reservoir. We are sometimes taking only part of the reservoir or some part of the coal seam. Okay, just like the methane extraction in development, you know that the limit is up to 3 meter. And then if any coal seam is having some 5 meter or 6 meter thickness, the latter part we are going to excavate or extract roof whitening method in the deep layering. Okay, in stages. Next is the porosity. Why porosity is important? This porosity is going to take place about the fracture system. Now, porosity of the pores and porosity of the fracture systems both are different. Okay, porosity is giving you the idea about the ratio of the void volume inside the solid, inside the total volume. So this void volume may be somewhat positions in have located in the pores, intermolecular spaces, or it may be located outside of the pore system, which is the discontinuity of the fracture system. So when I am telling about this porosity, it is about the secondary porosity. Okay, that's why it is always sometimes given primary porosity or secondary porosity, or just like the matrix porosity and the fracture porosity, to differentiate the two different concepts or the parameters. Next is the pore volume compressibility. Pore volume compressibility. Why this is important? Pore volume means the total void volume, you know, and this compressibility means with pressure how much expansion or the contraction is going to take place. Okay, here comes the bulk modulus. Here comes the bulk modulus, because it is very much related to the volume. The volume is obviously going to related with the permeability because of the Q. The volume rate or the mass rate is always related to the permeability. Then comes the fluid properties. Obviously, depending on the fluid, if there is a water viscosity, water density, water temperature, water flow velocity, whether it is laminar or the turbulent, so all those things will come. And similarly for the oil or the gaseous. And then is the drainage volume geometry. Drainage volume geometry means how your volume is going to be connected. Drainage volume means from where when you are going to take out the gases or the water, how much area is going to be covered, what is the shape of that area. Shape means whether you have put a grid pattern, just like the Boden Player Gallery in district, you are having a vertical depressed gallery and the horizontal level gallery. Okay, I'm just giving some crude examples so that you can compare the things and you can visualize, because until you visualize, you will not be able to understand the situation. So in the drainage volume also, suppose at some horizontal level, depending on the deep of the sea, you are going to get some grid pattern or the mesh type of structure. Okay, and the coal matrix is already having some mesh type of or the solid type of structure. It is surrounded by the facets and the buttons. It may not be square, but it is obviously rectangular pattern. So in that case, you have to see that what is the geometry, whether it is a rectangular geometry, whether it is a rhombus type of geometry, and how far area it is going to be progressed. Okay, So these are some of the initial considerations of the reservoir properties and the fluid properties that are actually going to govern the storage, which is related to the matrix, and the transport, which is related to the structure systems. Okay. In the next discussion, we are going to consider each of this in much more detail. And here you will get the total idea in a much more detailed way about whatever you have already learned and whatever you need to learn about this coal methane reservoir. So we'll start with the part one, properties that control the gas in place. Okay. Now, whenever you are going to see the properties, okay, in this area, what we need to discuss? We need to discuss about the obviously the gas storage place. What is the gas storage of the coal matrix? Okay, whatever is the total gas content and whatever is the total reservoir thickness. Okay, because these three are very important to estimate the gas in place. Okay. Now first come the gas storage in the coal matrix. So when you are going to know the gas storage about the coal matrix, the first idea obviously is for the Langmuir isotherm. Because if you don't know, if you are not having any Langmuir isotherm or absorption isotherm, it is established by the scientist Langmuir. That's why it is this option isotherm is also called the Langmuir isotherm. There are 6 different type of the isotherm, but this was the simplest. So just consider that this is the particular type of isotherm that is valid for coal and gas structure. Okay. The later forms will be going to discuss in the later. Okay. Now, as you know, the gas is primarily stored in the matrix surfaces, okay, and in an adsorptive state. So, the Langmuir adsorption is going to give you the idea, as you have seen earlier, about the idea about at particular pressure and the temperature condition, depending on the coal type, okay, how much amount of the gases can be stored, whether it is totally saturated or it will be partially saturated or whether it will be totally saturated. Now with this isotherm, you have to have, if you have this data, your most of the most of the parameters will be easier to find out based on this isotherm. If not, you have to do the laboratory testing. So once you are having this isotherm, the fundamental concept of the Langmuir isotherm is going to give by the equation 4.1, as you can see, gas storage capacity, and please also try to remember the units also. So GS is the gas storage capacity or soft gas capacity, is given by the VL. The VL is the Langmuir volume, and here mind that they have assumed the dry and ash-free basis. So DAF basis, dry and ash-free basis of the gas absorption. Okay. So VL is the Langmuir volume defined as the maximum capacity of the gas that can be stored, maximum gas storage capacity at some fixed temperature with infinite pressure. And then small b is the Langmuir constant, which is inverse of the Langmuir pressure. Okay. And then p, small p, is the reservoir pressure. Okay. Whereas this a and wc, a is the ash content and wc is the moisture content in the weight fraction, that means in percentage basis. Suppose you are not going to express this in DAF basis, then you have to remove all the element within the third bracket. Okay, you have to remove this idea. So your basic equation for the gas storage capacity is VL into BP divided by 1 plus BP. If I am going to give it in terms of PL only, so put B is equal to 1 by PL. Okay, and then you will get GS is equal to VL into P by PL plus P in terms of Langmuir pressure constant, Langmuir pressure. Okay, whereas if you are putting as in B, B is 1 by PL, which is the Langmuir pressure constant. Okay, it is also discussed in this text, as you can see here. Okay. So this is the Langmuir pressure constant. So this is the fundamental concept of the gas storage capacity. The P, this is established from the laboratory experiment. You are going to vary the pressure differently at some 5 or 6 pressure steps. So you will be noting P and you will be taking out the gas storage capacity by calculation of the real gas law, okay, by calculation of the material balance equation using the real gas law and other software for gas compositive value, okay. From there you will be getting six different pressure. You are going to get 6 different storage capacity, okay. So you are going to, when you are going to iterate this, when you are going to put this as a graph, you will be iterating and you can solve about the VL and the PL or B. So from the iteration, you are going to get finally the VL and the B. So the VL will give you the maximum capacity, storage capacity of this particular type of coal, and the pressure, Langmuir pressure, which is defined as the pressure corresponding to 50% volume of the maximum volume, maximum sort volume. Okay. So you will be able to calculate this graph and you will be able to plot this. Okay. Now there are some different factors which are going to affect the sorption isotope. Okay. So I think the time has come. So let us stop here. And so tomorrow's class, as you have agreed with me, you all are agreed with me that tomorrow also will be starting class at this 10 a.m. Okay.